Good day to each and everyone. This is Tehana Ibale of BSED Science 3 speaking. So for today's video, we're going to have a problem solving pertaining to the lesson 3 entitled Latent Heat and Phase Changes. In every change in state, heat is either added or removed from the body. The heat needed to change the state of a body is called the latent heat. Latent means hidden. The heat added during a phase change is used to break the bonds between the molecules and not to increase the kinetic energy and hence the temperature. The temperature of the molecules change in state or phase is never accompanied by a change in temperature. Change in state occurs at constant temperature. For example, the temperature of boiling water will not change though we continue adding heat. The heat added will be used to change boiling water to steam. Similarly, heat added to ice will not increase its temperature. It will just melt the ice. The temperature will remain constant until all ice is melted. In order for you to understand deeper the said topic, let me elaborate to you through showing you the step-by-step process with the sample problem I made. In solving the problem, we undergo 5 parts or steps starting from part A to E. So without further ado, let's get started. So now I'll present to you the sample problem I made. I'll read the problem. We get a 9.2 gram of ice in a freezer with its temperature at negative 15 degrees Celsius, and we apply heat to the ice continuously, assuming that no heat is lost to the surroundings. How much heat is needed to convert this ice to steam at 112 degrees Celsius? So let's find out the answer to the problem. Let's start in part A, where we will get the amount of energy present in our sample problem by using this equation. Q equals mc ice change of temperature. So before we solve it, we need to get the given first. The given are m, the mass of the ice, which is 9.2 gram, and we need to convert it to kilogram by simply doing this process. Times 1 gram divided by 1,000 kilogram. Cancel out the same unit. Then 9.2 times 1 equals 9.2 over divided by 1,000 kilogram. So 9.2 divided by 1,000 kilogram is equal to 9.2 times 10 raised to the power of negative 3. Copy the unit, which is kilogram. Next is the specific heat of ice is 2090 joules per kilogram degree Celsius. And the initial temperature of the sample problem is negative 15 degrees Celsius, and the final temperature is 112 degrees Celsius. So let's solve it. Q equals mc ice change of temperature. So substitute the given with the equation. The m is 9.2 times 10 raised to the power of negative 3 kilogram. The specific heat of ice is 2090 joules per kilogram degree Celsius, and the change of temperature, which we will have the final temperature minus the initial temperature. So 112 degrees Celsius minus negative 15 degrees Celsius. So let's solve it. 9.2 times 10 raised to the power of negative 3 kilogram times 2090 joules per kilogram degree Celsius. We need to cancel out first the same unit, which is the kilogram. So the answer is 19.228 joules per degree Celsius. Then the 112 minus negative 15 degrees Celsius equals to 127 degrees Celsius. So let's multiply them. So 19.228 joules per degree Celsius times 127 degrees Celsius. Let's cancel out first the same unit. Excuse me. So 19.228 times 127 is equal to 2,441.956 joules. So this is the amount of energy present in the sample problem. Let's go on to part B, where the temperature remains still despite of the energy being added. So in this part, we will solve for the absorbed energy by the melted ice using this equation. Q equals mLF. So we'll get the given first. The given are mass of the ice is 9.2 times 10 raised to the power of negative 3 kilogram, and the latent heat of fusion or of water, or the LF of water, is 3.33 rather times 10 raised to the power of 5 joules per kilogram, which we can find it in the table. So let's go on the solving session in part B. So Q mLF, so mass, let's substitute the given. 9.2 times 10, 3 kilogram. 10 raised to the power of negative 3 kilogram, then times the latent heat of fusion of water, which is 3.33 times 10 raised to the power of 5 joules per kilogram. So let's cancel out the same unit, which is the kilogram. So 9.2 times 10 raised to the power of negative 3 times 3.33 times 10 raised to the power of 5 joules is equal to 3063 rather 0.6 joules. The final answer is 3063.6 joules, which is the absorbed energy by the melted ice. So now let's go on to part C. Part C of the problem solving. So the energy added to the water increased its temperature, but still there are no changes in phases. It means we can use the same equation from step 1 or from part A. In part C, we will calculate the energy needed to increase the temperature through the use of this equation. Q equals mc water, change of temperature. So in part C, in part B, part C rather, we will calculate the energy needed to increase the temperature. So the given are mass of the ice 9.2 times 10 raised to the power of negative 3 kilogram. The seawater, specific heat of water, the 4.9 is 4.19 times 10 raised to the power of 3 joules per kilogram degrees Celsius, and the initial temperature is negative 15 degrees Celsius, and the final temperature is 112 degrees Celsius. So let's solve it using the equation QMC water, change of temperature. Let's substitute the given. The mass is 9.2 times 10 raised to the power of negative 3 kilogram. Next is 4.19 times 10 raised to the power of 3 joules per kilogram degrees Celsius. And the change of temperature, which is the final temperature minus the initial temperature. So 112 degrees Celsius minus negative 15 degrees Celsius. So let's calculate, or let's solve it. So 9.2 times 10 raised to the power of negative 3 kilogram times 4.19 times 10 raised to the power of 3 joules per kilogram degrees Celsius. So we need to cancel out first the same unit. So the answer of it is 548 joules per degree Celsius. So in the change of temperature, 112 degrees Celsius minus negative 15 degrees Celsius is 127 degrees Celsius. So before we solve it, let's cancel out the same unit, which is the degree Celsius. So 38.548 joules times 127 is equal to 4,895.596 or 596 joules. So it is the energy needed. The answer is, therefore, it is the energy needed to increase the temperature. So we're now heading to part D. The change in phases occur from water to steam due to rising temperature of 100 degrees Celsius, while in part B, the water-steam mixtures remain constant. So in this part, we need to calculate the required energy to convert the 9.2 times 10 raised to the power of negative 3 kilogram of water at 100 degrees Celsius of liquid to 100 degrees Celsius steam with the standard of latent heat of vaporization of water, which is 2.26 times 10 raised to the power of 3 joules per kilogram. So we will calculate it using the equation of Q equals mLV. We'll know that M stands for mass and LV stands for the latent heat of evaporation of water. And let's get the given first. Given are the mass of the ice is 9.2 times 10 raised to the power of negative 3 kilogram, and the latent heat of evaporation of water that can be found in the table is 2.26 times 10 raised to the power of 6. 2.26 times 10 raised to the power of 6 joules per kilogram. I made a mistake about the reading of the latent heat of evaporation of water lately. It is raised to the instead of raised to the power of 3, it is 10 raised to the power of 10 raised to the power of 6 joules per kilogram. So now let's substitute it through the equation. So the mass is 9.2 times 10 raised to the power of negative 3 kilogram times the latent heat of evaporation. Oh, it's LV. I'm sorry, made a mistake again. So it's LV, not LF. So LV, or the latent heat of evaporation, will be 2.26 times 10 raised to the power of 6 joules per kilogram. So cancel out the same unit, which is the kilogram. So 9.2 times 10 raised to the power of negative 3 times 2.26 rather times 10 raised to the power of 6 joules per kilogram is 20,792 joules. It is the required energy. To convert 100 degrees Celsius of water to 100 degrees Celsius steam. So now let's move forward to part E. So in this part, we will know the energy required to increase the steam temperature to 112 degrees Celsius. Energy required. Energy required to increase the steam temperature to 112 degrees Celsius. However, there are no phases changes. So to calculate the energy required, we will use the equation, which is Q equals MC. C, steam, change of temperature. The given are mass of the ice is 9.2 times 10 raised to the power of negative 3 kilogram. This is steam, 2.1 times 10 raised to power of 3 joules per kilogram degree Celsius. The initial temperature is negative 15 degrees Celsius. The final temperature is 112 degrees Celsius. So let's substitute the given with the equation. MC steam. So the mass is 9.2 times 10 raised up to the power of negative 3 kilogram. The specific heat of steam is 2.01 times 10 raised to the power of 3 joules per kilogram degrees Celsius, and the change of temperature, which is final temperature minus the initial temperature, is 112 degrees Celsius minus the negative 15 degrees Celsius. So let's cancel out the same unit first before we solve it. So 9.2 times 10 raised to the power of negative 3 times 2.01 times 10 raised to the power of 3 joules per degree Celsius is equal to 18.492 joules per degree Celsius, while the answer to the change of temperature is 127 degrees Celsius. Cancel out the same unit, so the final answer will be 2,348.484 joules. So it is the energy required to increase the steam temperature to 112 degrees Celsius. So we are now in the last part of the problem solving. So after solving from part A to E, we will get the total absorbed heat energy starting from ice at negative 15 degrees Celsius to steam at 112 degrees Celsius by adding all the absorbed energy from A to E. Part A, Part B, Part C, Part D, Part E. We're going to write it here, the answer in every part. So in part A, 2,441.956 joules. In part B, 3,063.6 joules. In part C, 4,895.596 joules. In part D is 20,792 joules. In part E is 2,348.484 joules. So let's sum it all. So the answer, or the overall answer, is 33,541.636 joules, or let's round it off to 33,542 joules. So it is the total absorbed heat energy starting from ice at negative 15 degrees Celsius to steam at 112 degrees Celsius. So the answer is 33,542 joules. So I hope you all learn from my discussion. So see you next video, guys. Thank you for watching. God bless.